Hello everyone, my name is Prateek Arora and I'm a PhD student with the Robotic Workers Lab of the University of Nevada, Reno. In this video, I will present our work on environment reconfiguration planning for autonomous robotic manipulation to overcome mobility constraints. This work is motivated by the wide range of significant mobility challenges found in real-world settings which are encountered during search and rescue and/or reconnaissance missions into disaster zones or other unstructured natural environments. Such settings are infamous for their mobility challenges at such scales that even the state-of-the-art robotic systems cannot overcome. More specifically, despite the fact that the robotic locomotion has reached unprecedented level of versatility, it remains focused on navigating around or over the environment structure. Hence, there may exist environment configurations which present large physical obstructions which have to be removed, or contain significant structural gap that have to be overcome. Particularly in the latter case, we care for scenarios when the lack of ground support structure is significant, such that the robot locomotion alone cannot jump over the gap. In such cases, we propose that a solution can lie in considering the surrounding structure as dynamic and leveraging free entities within it as tools that may allow us to reconfigure the environment in order to bring it to a state that unlocks novel navigation routes. Accordingly to this context, we determine that a robot's operating environment may present the following classes of mobility constraints. Either significant structures that are a part of rigid environment structure, such as the terrain or obstacle collision volumes which should be avoided, or floor gaps which correspond to lack of ground support points to stand on. Within our presented work, regions of the latter class are considered to be potential fill-in opportunities, that is, as long as there is a potential to bridge the corresponding gaps by reconfiguring the environment structure, these may offer potential navigation alternatives for an autonomously exploring mobile robot, allowing it to escape into novel and originally unreachable regions. Our problem formulation comprises of two subproblems. Traversability gap detection. This refers to the ability to identify gap regions of the terrain's traversability map, whose structure and size can potentially restore connectivity between two separate regions if they can be successfully filled in. And environment reconfiguration planning. This refers to the ability to first analyze the identified pocket to determine its physical structure as occupied, free, and boundary terrain layer voxels. Second, plan to position a known tool-like object in a valid, physically consistent, and stable configuration that respects the geometry of the gap. And finally, evaluate whether the planned configuration results in reconfigured state of the environment that extends traversability to an originally unreachable region. For a proposed method, we assume that the robot is already performing a variant of next best view based exploration planning autonomously. The robot also relies on a pipeline for mid-range traversability estimation and graph construction regarding the environment terrain, which we will present shortly. As soon as exploration becomes stuck, that is, there remains no traversable path that leads to further exploration gain, then our proposed pipeline is engaged. This starts by estimating an extended traversability map which acts as the foundation to identify gap regions and subsequently plan to fill them in using objects in the environment that may be picked up and used as tools. Per standard practice, we consider a 3D volumetric map representation containing occupied, free, or unknown status voxels. We additionally consider a Euclidean sign distance field representation where each 3D point holds the value of Euclidean distance to the nearest occupied voxel. We define as admissible robot configuration. A configuration where the robot's frame of reference stands at least at a clearance distance RC away from the nearest occupied volume, and its Z coordinate is the lowest compared to any other ESTF point, which means that from the map points, it is the one closest to the ground. The value of RC is the distance between the robot's frame of reference and its virtual footprint. Accordingly, we define the set A of all admissible robot configurations as a subset of the ESTF map F. Ground support. A 3D point XQ is ground supported when it has a vertical clearance up to a depth D and is underpinned by an occupied structure beyond D. This means that a ray projected vertically downwards from xq up to a maximum depth of dmax, the voxels from the point xq to xd will be free and the voxels at the point xd will be occupied. Reversibility condition. A robot at configuration Xi is assumed to have k number of ground contact points, where k is equal to 4 in the case of four-wheeled robot. The entire robot is defined to be ground supported as long as all the ground contact points are. We also define for a small transition edge between two robot configuration is traversable as long as the robot is ground supported for both and they differ in no more than RT in elevation. A complete mid-range terrain traversability estimation relies on a 2 plus 1D graph which we construct based on the previous definitions. Initially, we construct a hash map which retains the lowest elevation values for the admissible robot configurations and provides fast access by 2D coordinates. The following steps aim to significantly reduce the search space for traversability computation. We subsequently construct a 2 plus 1D graph G, whose vertices correspond to the entries of the admissible robot configuration subset and their elevations, and its edges correspond to the traversable robot transitions. At this point, we only check in a star-connected fashion for transitions that differ by no more than RT in elevation. We then isolate the graph-connected components that contains the robot's root configuration, that is, only the part that is potentially reachable by the robot. We then proceed to calculate the ground support condition for all contact points per configuration within the isolated connected components only, effectively pruning any untraversable edges. This pipeline is used to perform both autonomous traversability-aware navigation as well as the process of traversability gap detection when the exploration gets stuck in order to identify regions that lend themselves to bridge the disconnected components of G. For the latter, we derive a 2D image projection of graph G where each pixel represents the Z coordinate value. We perform morphological closing and black hat on its binary version to derive candidate traversability gap regions. We follow by fast marching base in painting on these masked regions, a process which performs normalized weighted sum filling of the values of missing pixels based on the neighboring known ones. For mostly uniform regions, the filled-in gap values will be the same as the surrounding ones, while in significantly skewed elevation regions, the values will follow steep inclines or declines. Based on these values, we construct a different extended traversability graph GE by overriding the real admissible set where the traversable edges that are corresponding to the infilled coordinates are marked as extension edges EE. For each frontiers of the extended graph GE, we perform Dijkstra's algorithm to find the shortest robot path from robot root to the frontier, and we select the one that offers maximal exploration gain. Since exploration was previously stuck, this path will lead to areas that were previously considered disjoint from the currently traversable graph. This path is divided into a reachable, an extension, and an unreachable segment. The extension segment corresponds to the first encountered extension edges, which are the ones required to be achieved by reconfiguring the environment in order to unlock access to the originally unreachable segment. The second problem of environment reconfiguration planning initiates as soon as the candidate extension segment region is identified. The goal region is visited and closely inspected by the robot to perform high accuracy structural mapping of its geometry. For every vertex corresponding to an extension edge endpoint, we perform ground support checking for all the ground contact points. For those that are unsupported, we extend the vertical search to a depth dscan, which is greater than dmax, to determine the underlying structure of the gap. At the same time, we build the unique voxel set as follows. Free boundary voxels shown in yellow that lie directly under the unsupported contact point. Free missing voxel shown in blue that lie below the boundary ones. Structure voxels shown in magenta that are occupied ones. These sets structurally characterize the terrain gap pocket. We assume that the robot is capable of identifying and picking up free entity in its environment whose 3D geometry it is capable of estimating autonomously. We conduct exhaustive search over different transformations of the object's reference frame. The goal of environment reconfiguration planning is to obtain those reachable goal configuration where the robot may position the tool-like entity such that they are A. Geometrically valid, that is, the object volume will not collide and penetrate into occupied structure and it will only occupy free voxels once positioned. B. Physically consistent, that is, it has at least a number of S ground supporting voxels underneath it. In our case, we consider S greater than 2 to ensure stable configuration. And C. Kinematically reachable. For the surviving valid tool configuration, we construct a test traversability graph GT by updating the original graph G until a candidate path that intersects the unreachable path is encountered. This is considered as a successful evaluation of the plan, and therefore the corresponding tool transformation is subsequently forwarded to the mobile manipulation kinematic planning policy for execution. For experimental demonstration, we deploy the algorithm on an autonomous mobile manipulation system, which is equipped with all the required perception, computation, and manipulation capabilities, as well as the capacity for autonomous real-time simultaneous localization and mapping, exploration, and traversability-aware path planning, as well as manipulation motion planning. It is highlighted that no external motion capture support system were utilized. To test the pipeline, we developed a corresponding experimental mock-up environment of a constrained bridge-like passageway that contains a gap in the terrain structure. Due to its geometry, it is impossible for this robot to fit beside the gap or cross over it without its wheel getting trapped into the ditch. The robot begins its autonomous exploration mission of an initially considered as unknown environment by incrementally reconstructing the volumetric representation of its surrounding. From the very start, the space is configured to trap the robot. At the same time, it derives the mid-range traversability graph in real time, which is leveraged to identify potential gap regions that, if restructured, may allow it to escape. Here, the graph edges are depicted in red. Dijkstra's path to all the frontiers are represented in yellow markers. The bridge gap is correctly identified as a potential traversability extension region, and the corresponding extension edges crossing over it are marked in cyan. The robot grasps a known tool-like entity. It is mentioned that the geometric knowledge of this timber log is provided a priori, but localizing it in the environment and grasping it are performed autonomously by the robot. The robot approaches the candidate traversability extension region and conducts close-up accurate inspection and structural characterization of the terrain gap pocket. The exhaustive search results over all considered test tool configurations is visualized here. Subsequently, only the geometrically valid non-colliding ones, and then the physically consistent stable ones, and finally, the surviving ones that actually restore traversability to the unreachable areas after the final test graph evaluation. Lastly, the robot plans and executes a kinematically valid and collision-free arm trajectory that achieves the desired tool placement, successfully restoring the terrain traversability to the other side of the gap. Thank you for your attention. Please feel free to ask your questions or contact us for any further discussions.